We'll deal with that in a second. We have liters of hydrogen. So it's liters of, yes, H2. It's H2, not H, because it's diatomic. What information are we given to start with? So we compare across. Are grams of aluminum the same unit as liters of hydrogen? No. So we're going to have to do some conversion factors in here. Very first thing I would typically do is try and get rid of grams of aluminum. Can I convert the grams of aluminum to liters of hydrogen? That is an invalid conversion. I cannot change substances with those units. So what do I need to use as my conversion factor? Moles. So I can convert it to moles of hydrogen, of aluminum. Right. There is no relationship between the grams of aluminum and the moles of hydrogen. Where do we get that conversion factor from? How many of you just know the molar mass of aluminum? Okay, just checking. So we're looking at, I would just call it 27, but since we're going to get specific on this, 26.98 grams of aluminum. Those of you moving into 151, yes, you should write down all of those significant digits. For the sake of the final, you are probably okay just calling that 27. We are now in units of moles of aluminum. Is moles of aluminum the same thing as liters of hydrogen? No. So what do we have to do? We have to convert. Can we convert the moles of aluminum into something of hydrogen? We can get the moles of hydrogen by using our balanced equation. So we can go up to our equation, and I see 1 in front of all of those, so I can just say 1 and 1, right? Why no? It's not balanced. You have to verify that it's balanced every single time. So to go through and balance this, so we got the chlorines fixed. Hydrogens would then come out at 3/2. This is a weird one, right? I mean, now it's balanced, right? Everybody see that? Nice and balanced. But 3/2. Okay, 3/2 is a bit odd. Okay, so there's a couple ways we can dodge that 3/2 statement. If this is 1 molecule of aluminum, 3 molecules of HCl to produce 1 molecule of aluminum chloride and 3/2 a molecule of hydrogen, that is a problem, because I can't have half of a molecule. But what if I change the unit to moles? Can I have 3/2 of a mole? Yeah, moles are a massive number. I can have half of a mole. Okay, so depending on the unit we're using, we may be able to get away with doing this. Okay? Because fractions are officially not supposed to be showing up, okay, which technically they can, what we need to do is find some way to balance that 3/2 out. Okay? To maintain the ratio of balancing, what I can go through and do is multiply the whole equation by 2. So that when I multiply 3/2 by 2, it becomes 3. So let's check that. 2 times 1, 2. 3 times 2. What am I doing? 2 times 1. 2 times 3/2. Is my equation still balanced? Okay. We can go through and check and verify that, yeah, that is still balanced. Okay. So you can do this multiplying through by 2 to get to your whole number ratio. If you end up with some weird thing and you don't like dealing with fractions, start balancing at the hydrogen instead. I'm not even sure that'll work. Yeah, you kind of have to go through the fraction method. Sorry. Okay. What does that mean then? What number shows up in front of moles of hydrogen? 3. What number shows up in front of moles of aluminum? 2. Anybody remember what those numbers were originally before we multiplied through by 2? It was 3/2 a mole of hydrogen, and it was 1 mole of aluminum. Does Why are we pointing this out? 3/2 divided by 1 is 3/2. It's the exact same numbers. So when we're dealing with mole values, we can cheat and use these fractional systems. If we're looking at molecules, that's where it gets odd. In 130, we seem to insist that you can't use fractions. It's not that you can't use fractions, it's that fractions tend to confuse people when you're looking at molecules. We aren't looking at molecules. Okay? We're now in moles of hydrogen. Is moles of hydrogen equal to liters of hydrogen? No, so we have yet another conversion factor. What is the conversion between moles of hydrogen and the liters of hydrogen? 1 mole of hydrogen is 22.4 liters. We could crank that all out and we'd end up with the liters of hydrogen. Just to be obnoxious, this reaction,
Where did you get the 22.4?
talk about that in just a second, was done at 32 degrees Celsius. Where did the 22.4 liters come from, please? 1 mole of gas is equal to 22.4 liters. This was one of the things that we just kind of assumed, not assumed, but used as our relative relationships between our liters and our moles. This is because one of our assumptions when looking at gases is that gases do not occupy any volume. So it doesn't matter what gas I put into a container, I'm going to end up with the same number of molecules within it because none of the molecules take up that volume. So we can get an exact relationship between the moles and liters of a gas, of any gas. Okay, so it's kind of a neat little feature out of this 22.4 liters. But someone did add an extra caveat to this. When is 22.4 liters equal to 1 mole? At standard temperature and pressure. Standard temperature is 1 atmosphere, or sorry, standard pressure is 1 atmosphere, and standard temperature is 0 degrees Celsius. If we're now at 32 degrees Celsius, does that equation work? No. So what ends up happening? We'd have to do a whole nother conversion factor that takes into consideration the effects of pressure and temperature.
So since that,
Right? Since
that pretty much never happens, what's the relevance of that? I mean, when is pressure and temperature going to be?
Oh, when are we at STP?
Yes.
Yeah, we're never at STP, which is one of the reasons why I did not mention this conversion factor earlier in the semester, because it's pretty much useless. Okay. It shows up in Chapter 8, and it shows up in Chapter 9 when you're looking at volumes of gases. Okay. It only holds true at standard temperature and pressure, which is very, very rare.
Pretty much only in a lab.
Right. When you run an experiment in the lab, how many of your experiments were run at 0 degrees Celsius? None of your experiments were run at 0 degrees Celsius. You could theoretically build a system to trap that, and that's where this kind of theoretically comes in. So ultimately, it shows up in your textbook as here's an extra thing to memorize so that we don't have to explain it to you. And what we'll do is always fix the question so that this never occurs. Okay. I keep getting the chapters confused. I think it's Chapter 10. Is that gases?
Sure.
Okay. Chapter 10 on gases is where we now actually talk about this and say that that conversion factor technically does not work if we're running this at 32 degrees Celsius. We'd have to come up with some other way to see that relationship. And that's partly what Chapter 10 is getting at, is looking at that other conversion when looking at gases. Okay? And we will talk about that today. For the sake of this question, if we were going to attempt to solve this, you would assume that you are running at standard temperature and pressure, because it is not specified. The only time where you would not assume is if one of your multiple choice answers was impossible to determine. Because if you don't know if it's at standard temperature and pressure, you don't know the relationship between the volume and the moles, and you would say it is impossible to determine. We don't have that information. Kind of makes sense? Very, very rare for that to pop up. You might see that as kind of a trick question in 151. 130, we're a little bit more straightforward, making sure you're aware of it, but that's about it.
I was going to make sure the final is going to have this and have impossible to determine.
You're not going to see that. They're asking you to go through and solve. So, atmospheric pressure. Or sorry, were there questions on that? I hope there weren't. Were there questions on that? Is there a question?
Are we done solving? Because I thought we were assuming it was STP.
We were assuming it was STP. And if it is at STP, you just directly solve through with those numbers. Yeah. If it's not at STP, we don't have the conditions yet to discuss that. And we'll talk about that in a little bit.
What is 1 atmosphere? What's the measurement?
What does 1 atmosphere mean? What does 1 atmosphere mean? Any ideas?
1 atmosphere above you.
It's like 6 feet or something, isn't it?
It's the pressure that we feel at sea level on this planet.
What's the unit?
Atmospheres.
Atmospheres? We do convert it back to something more.
You get all sorts of conversion factors coming out of pressure, which I think is also in here since you're asking about it. Yeah. Right. The atmosphere unit is the one that I tend to use the most often because the number associated with it is 1. That's really easy. Right? There are all sorts of other units that can pop up in here. The history of it comes from mercury. And in fact, it comes from, I think, millimeters mercury. So that's what this experiment was designed to do. You took a tube of mercury, you inverted it into another container of mercury, and you noticed how far the mercury fell within that inner tube. Because gravity is going to start pushing down on the mercury, or pulling down on it. At the same time, atmospheric pressure is pushing down on the liquid, which then keeps the liquid inside the tube. So the balance of gravity and that external pressure, or atmospheric pressure, we can then visualize and monitor or quantify by the height of that mercury tube. Okay. Why did we end up using mercury as opposed to any other substance? Okay. If we put a container of water out on the counter, what happens to the container of water?
Vapor pressure, right?
It eventually disappears. It all turns into a gas. Okay, well, that's fantastic. We're seeing a nice transition from the liquid to the gas phase. We've seen that before when we heat it up to 100 degrees Celsius and it reaches the boiling point. If we just put the container of water out on the table, do we reach the boiling point? No. At no point does it ever reach the boiling point. So why is it disappearing? What that has to reference is something known as vapor pressure. All liquids have a vapor pressure associated with them. When we looked at the melting point is literally breaking the intermolecular forces away from each of the molecules. That's what happens at the melting point. The boiling point is a slightly different system. We've already broken all the intermolecular forces. So why are those molecules now still being held close to each other? Okay, well, if there's nothing holding them there, shouldn't they be a gas? We should really only have 2 phases, solid and gas. What is that liquid phase? Water is an example of the liquid phase. Why do we have a liquid? What is keeping those molecules close enough each other? There's a weak connection, but there's another aspect to it. It's not just the connection between the molecules. Something else has to be keeping those molecules near each other.
So it's not atmospheric pressure.
It is atmospheric pressure. The boiling point is not just a measure of the intermolecular forces between the molecules. It is now also a measure of atmospheric pressure. Okay. Do we know this to be true? Well, you boil a pot of water at the ocean and you boil a pot of water in Denver. What's the temperature of the water in both those cases? Sorry. It is different. It is not 100 degrees in both cases. Okay. It is 100 degrees at sea level. In Denver, 98-ish. It's dropped its boiling point, which is one of the reasons why when you cook at altitude, you tend to have to cook things longer. Why? You're cooking at a lower temperature. It requires more heat to get that process to actually cook and cook all the way through. Yeah.
Question. So say if you went in the ocean below sea level quite a bit, would
Yep.
it be quite a bit less for boiling point, or would
What's,
it be more?
do you have more pressure or less pressure when you go under the sea? More pressure, which means what's going to happen to your boiling point? It's going to increase. Exactly right.
The ocean floor, the water temperature is 600 degrees.
Okay, I'll accept that. I don't have any way to refute that, so sure. So what we've got is all sorts of pressure gradients now incorporating into our boiling points. Okay? So when we go through and look at a liquid, it's not just sitting there as a liquid and we're waiting till we have enough energy to turn it into a gas. It is already turning into a gas. Okay? So that if I take a container and I fill it up with water, eventually that all disappears. But what happens if I put a lid on it? Why does it now not all turn into a gas inside that container? What's that?
It's trapped, it's contained.
Creates
It's not.
The pressure is,
There it is. Okay. That liquid is turning into a gas. As it turns into a gas, what happens to the pressure inside the container? It builds to the point that now what happens at the boiling point? It gets even higher. So the whole thing can't vaporize because our atmospheric pressure is now pushing down even harder against it. Okay? So when you open most containers, you tend to hear a hiss. Why? It's that external pressure being alleviated, okay? or that internal pressure being released. So when we look at a liquid open on a surface, we are constantly having that liquid turn into a gas. Okay? But by that same token, that gas is also turning back into the liquid. It's in, if you will, an equilibrium between the two phases. Okay? So why is it that we see all of the liquid all of a sudden disappear, or not all of a sudden, but over time disappear if we have an open container?
It's not an equal amount that's being transitioned.
With that open container, what blows across the top of it?
Air,
What is that air grabbing?
vapor.
Some of that vapor. There is now no gas particle above the liquid. So what does the equilibrium now shift to do?
Push out more.
Make more gas. Air continues to move across, and it continues to move that gas phase out of the way. Eventually what happens? All of the liquid water gets converted into gas because it's just trying to balance out the equilibrium between a liquid and a gas. If we constantly remove the gas product, we're going to constantly reduce the concentration of the liquid. It's going to keep moving over to the gas phase. What happens if I add more gas in there? If I increase the pressure on a gas, what happens to it? Goes back into a liquid. Okay? So if I can put in enough pressure behind a liquid, I can push it over into, or enough pressure behind a gas, I can convert it into a liquid because we're looking at the balance of that vapor pressure. The vapor pressure to the atmospheric pressure. The vapor pressure is coming from the liquid, the atmospheric pressure is coming from the gas.
So is that how like aerosol cans work? Just the pressure of the...
We can see aerosol cans. I would argue there's a better example. There are people that carry around canisters of oxygen, right? Why are they carrying around the canisters of oxygen?
Breathe.
So they can breathe better. Okay? If they are just carrying around a canister of gaseous oxygen, they're going to run out of oxygen really, really quickly. What are they actually carrying around? Liquid oxygen. We've put enough pressure behind that container, or the gas within that we've forced all of that gaseous oxygen to turn into liquid oxygen. That now increases the density, and we get a lot more oxygen out of that individual container. Okay? What does that mean about the container? How strong does it need to be? It needs to be incredibly strong to withstand that pressure that we've now had to force on it to keep it in the liquid phase. Thus, when you try and, that container now has a lot of pressure pushing against it. And one of the things you end up finding is that at the top, at the valve, that's the weakest point. And so you can hit or break those which is now going to cause all of that liquid oxygen that was staying a liquid solely because of the pressure. Now there's no more pressure. So what does the liquid do? It immediately turns into gas, and what we end up having?
Torpedo.
A little torpedo rocket thing. All sorts of fun. Okay? No. Okay. You can go to YouTube. In fact, I think even Mythbusters did a thing on it before, too. What's that?
Put it like through a wall.
Yeah. There's an insane amount of pressure behind it. Okay. Yeah.
What about in space? I wanna-
What about in space? I need
As
some
far
more.
as atmospheric pressures and all that. and-
So what happens to the boiling point of water in space? What temperature is it? It's very, very low. There's now no pressure on the outside keeping that phase a liquid. So what ends up happening? It instantly vaporizes. So if we took solid ice out into space, what happens to it? It goes from the solid to the gas, and we don't see a liquid phase.
How do you drink up there? I'm not
Viscous water.
a space expert or anything.
Are
How
they
does that
drinking outside their spacesuits or the space station? No, they are drinking within the space station or within their space suits. Guess what they need within each of those conditions? A massive amount of oxygen and air to provide enough pressure to have things function at normal levels. Our body functions according to certain atmospheric conditions. What happens if we didn't have a spacesuit? All of our liquid now wants to vaporize. That becomes a bit problematic in space. Right? At least if you wanted to survive. Okay? So yeah, you're going to get all sorts of nasty things happening in that case. So vapor pressure is an important concept. So if we think back to the original experiments, they used mercury instead of, say, water. Why? We have an open container to test the pressure. Right? If that is an open container, what does that mean if we used water? That water is now constantly evaporating out of that bottom section. If the liquid down here starts to disappear, what happens to the liquid in the tube? It drops. Is it dropping because the pressure has changed or because the vapor pressure of our liquid has changed?
Yes.
The vapor pressure. So it's too hard to correlate atmospheric temperature changes or atmospheric pressure changes versus vapor pressure changes. So we pick a substance in these these pressure chambers that has a very low vapor pressure, so much so that we can ignore it. Mercury happens to be a liquid with very low vapor pressure, meaning that when we have this open condition or open container, we don't see a lot of that mercury turning into a gas, which means the only thing that's causing the change in that height is atmospheric pressure, not the evaporation of the mercury itself. Hi? I don't know. Hi. So vapor pressure is the pressure exerted by any liquid or any substance above a liquid. Okay? It's it going into the gas phase. So let's take a look at some examples here. Let's see if we can predict these based off of my favorite section that nobody seemed to like, but we're going to talk about it anyway. Water versus methane. Which one would we expect to have the higher vapor pressure? Not a bad guess. But let's say we can ignore our gas phase. We're saying we got these both in a liquid. In fact, we can push this even further. Forget, butane's not a... butane we can get in a liquid, right?
Yeah.
There we go. We got butane versus water. Now we don't have that whole gas phase issue. Which of these would we expect to have the higher vapor pressure?
Butane.
Why butane?
It's a lot bigger.
Well, it doesn't have to do with size. The vapor pressure is our liquid molecules busting away and saying, F you, I don't want to be with you anymore, I'm going to go be by myself. What has to break to be away and by itself?
Soda's heart.
What was that, Natalie? Close, not the bond.
Force.
The forces between those individual molecules has to break.
It's the same force.
Is it the same force for each of these molecules? Shaking your head? Why? What's the force in water? We get hydrogen bonding in water. What do we get in butane? London dispersion forces. Okay. Which of those two forces is weaker? London dispersion. Which means for butane to go up in the gas phase, I just have to break an incredibly weak force. For water to go up into the gas phase, what has to happen? Break a much stronger force. Which of these two would I predict have a higher vapor pressure? Butane, the one with the weakest intermolecular forces. Remember how I said forces were really important? Ta-da! I guess that wasn't fancy enough. Ta-da!
How long did it take you to memorize all of, like, butane?
I'm not sure you want me to admit that, but I knew that in high school. That was part of my high school education. If it makes you feel better, the naming part of it that I learned in high school, I then very swiftly decided was irrelevant when I moved to college and didn't bother to learn anymore. So, what about dissolving gases in liquids? So now we're looking at a new substance. I want to take CO2 and I want it to dissolve in water. What do I have to do to get that gas to now dissolve? I'm not turning it into a liquid, but I'm putting it into a liquid. What do you mean by pressure?
You can put pressure on it.
Why do you have to put pressure on it?
So then it can change again.
Pull everything.
Our gas is constantly moving around, doesn't want to touch anything. What happens when you dissolve it in a liquid?
It has to stay with the liquid.
It's touching all of the liquid molecules. So how do I get the CO2 forced into that situation? I have to put in a high external pressure to force the gas into that liquid system. So a high pressure is incredibly important to get this to dissolve. Which is why when you open up your soda, what happens? Not only is it just a psst, but then what do you see happening? You guys said it first. Why are you all laughing when I say it? What do you see rising through the liquid? You see bubbles. What's happening? All the CO2 that was forced into the liquid is now also coming out of the liquid because you've reduced that pressure. Is there anything else that controls how much gas you can dissolve into a liquid? The what? Bond? Okay, I can see where you're going. Bonds and forces. Remember, we are now trying to force an interaction between two particles. We're saying you must talk to each other. You have to interact. Okay? So we can look at an external pressure forcing them to interact with each other. What's another thing that could, say, prevent them from interacting with each other? No. Conditions. What happens if we heated up this room? Where are you all going to move to? As far away from each other as possible, right? Okay. What happens if it gets frigid cold in here? What are you going to do? You're going to start to gather up. Why? Get the residual heat that everybody else is giving off to help keep you warm. What's happening in this system? Same idea. What happens when you heat up that soda? You forgot your can of soda in the car during the summer. What happens when you get back to it? It's all over the car. Why did it explode? It got so hot that this CO2 that we forced into the liquid said, I don't want to be in with the liquid anymore. I'm going to turn into the gas phase. So it starts coming out of the liquid as quickly as it can. Eventually, what ends up happening? The container that we designed to hold that gas in there fails, and it explodes soda all over the car. How often do you have a soda exploding in your fridge?
What happens in the freezer?
We'll talk about that in a second issue, a second case. Was it a soda that you made and fermented?
No.
Okay, that might be a little bit weird.
Really, I've seen that too.
So typically, to get something to explode at cold temperatures, something else is happening. We're producing secondary gas. And that does happen rarely, but that's a secondary issue to this. If we pump in a consistent amount of CO2, it should never explode in the fridge because there's no reason for it to. Okay? The gas wants to stay dissolved at that temperature. So as soon as you heat it up, what happens? All the gas then comes out of the solution and into the gas phase, and we no longer have the gas dissolved. If we want to reverse that process and shove more gas into a liquid, we have to put in a lot of pressure and we drop the temperature. Okay? That's how we keep it sparkling, if you will. I didn't think it was that funny either. Easy crowd today. Questions on that?
What about the freezer?
Okay. What's happening with the freezer? Anybody know that one? It is not the gas that is causing the explosion in the freezer. It's the liquid. What's special about water?
It expands when it's frozen.
It expands when it's frozen. It's one of the few liquids that actually does that. Arguably, that's also one of the reasons why water or life on this planet can exist. Okay? Because as we increase pressure, it melts, okay? Which means, and then also our ice expands and takes up volume, which means it becomes less dense than the liquid, which means where does our solid phase ice exist? On the surface of water as opposed to on the bottom. Okay? So big contributions for why we end up seeing life is because of that property of ice. Ice actually expands its structure. So if you put a soda into the freezer, yes, it explodes, but because the ice is freezing and causing it to break the container. It has nothing to do with the gas or vapor pressure.
How come alcohol doesn't freeze?
It does. Alcohol does absolutely freeze, but does it freeze in the freezer? No. Why? Your freezer's not cold enough. Alcohol will freeze, you just have to get it to a colder temperature. I would be surprised if it's the alcohol. It's probably the water in the alcohol that's freezing.
Why is it when you like put beer in a cooler and then you put the ice and then you put salt in the cooler, it like gets
Deep
real?
I will leave that for 151. The salt affects the freezing point and boiling point of liquids and solids. So if you really want to talk about it, there's all sorts of math and junk with that I don't really care about. Okay, so units of pressure. We already mentioned a couple. Millimeters mercury, 1 atmosphere. Okay, there are several others. You've got torr. What else do we have? PSI, kilopascals, pascals. If we've got a length measurement, millimeters of mercury, of course we can then have centimeters of mercury, which then also means we can also run into inches of mercury. All of these are valid units for pressure. Which one do we typically use? Well, depending on your instructor, they'll pick different units. The one that I tend to stick with is 1 atmosphere because it's a very easy number to remember. You tell me to remember the pressure at sea level in torrs. Is it 760?
Yep.
Yeah. Oh, but I didn't know the unit on that. Dang it. Oh, no, I did. Torrs, 760 torr. There we go. What was that? Torr is named after the person that invented that unit for pressure.
So it's like a calendar?
Yeah, kind of that idea. So you are responsible officially for being able to interconvert between all of those different units of pressure. It's the same kind of conversion systems that you guys have gone through and done already. It does not explicitly show up on the final. I think I even removed those questions maybe from the homework. Anybody done the homework? Nobody's done the homework? Okay. It's not like that's due on Friday. Just saying. Isn't it due Friday?
Yeah.
Oh, it's due Thursday.
No, it's due Friday.
I don't know what day that is. It's Friday. Okay. So you should be going through and doing some of these. I will say that the acid-base chapter with titrations, remember that titration calculation that we went through and did already? There's a few like that. So I tried to limit those again, but each of your homework assignments are sitting at about an hour, okay, according to their predicted length of time. So you're looking at, for the homeworks, I think it's 2 homeworks, which will be an hour apiece, and then there's the reading assignment. Those are like 10 minutes. Those are just reading multiple choice answers. Okay, so you're looking at least 2 to 3 hours probably to complete the homework. If you haven't started that yet, you should probably get that going.
Yeah.
Ideal gas behavior, we keep talking about this. The no volume is the important one. That's how we get 22.4 liters equaling a mole. Other random things that we kind of get out of this, gas molecules move in random directions. They are not attracted to each other. Okay, so when we're in the gas phase, there is no intermolecular forces anymore. That's one of our big primary assumptions. Another big one is they collide without losing energy. So you smack 2 atoms near each other, they don't just kind of absorb that shock and both of them stop moving. They then bounce perfectly off of each other. Okay. Average kinetic energy is proportional to the temperature. Okay, what does that mean? If I increase the temperature, what happens to the kinetic energy? It increases. Kinetic energy was a measure of motion. How fast are your particles moving? So if we increase temperature, we're going to move a lot more too. Okay, so we can see a proportionality out of that. So let's take a look at the variables that affect gas pressure. There are 3 variables. We've actually already talked about all of them. Temperature. How is temperature related to pressure? As temperature increases, our pressure also increases. If we're going to try and set this up into a mathematical expression, what we would do is say temperature, that little alpha symbol means is proportional to pressure. You increase temperature, pressure also goes up. 1-for-1 relationship. And I wrote that way too big, so I'm going to erase all that. What else? So atmospheric pressure is pressure, though. Okay, so we aren't now looking at the liquid. We aren't concerned about vapor pressure at this point. What other things can contribute to pressure? What's that? Okay, volume. If we change the volume, does the pressure change? Yeah. Okay, how does it change? If we decrease the volume, what happens to the pressure? It increases. Think about a random balloon. You take a balloon and you try and decrease the volume. To do that, you have to now force everything down on that balloon. What eventually happens? The pressure increases so much that the balloon pops. It fails against the pressure against it, and it explodes. Okay? So we have an inverse relationship. Okay, so we'll call this direct. This is inverse. How would we write that out in our nice little mathematical expression?
V is negative proportional to P.
Negative P doesn't quite work because can we have a negative pressure? Remember, pressure is the ability of a particle hitting against something else. Can we have the pressure of a particle that's not hitting against something else in a negative fashion?
What?
No, so we can't bring in the negative. So how do we get that inverse relationship? What happens is we increase pressure. What happens to the volume? 1 over a really big number gives us a really small number. So if we increase pressure, volume decreases. There's our inverse relationship. What's the last thing that contributes? Right idea. What do you mean by substance? So it's a direct relationship. Phase doesn't quite work because we're looking at pressure, and ultimately our pressure is all in reference to gases. Okay? We can kind of bring that in, and that if I have a solid what is the amount of gas? 0. So what's the pressure? None. What happens as I turn that solid into a gas? What happens to the pressure? It increases because there's now gas particles to push against it. What happens if I continue to turn that solid into a gas? What happens to the pressure? It continues to increase. What is causing that increase in pressure? So here's our container. There's our solid. When we started, there was no gas. It was all just solid. What's happening as I turn that solid into a gas? I erase some of that, and I now have gas. What happens as I continue to remove that solid?
Forces.
What changed? Kind of, not quite the phase. Right idea. What's taking up the space? The gas molecules. The number of molecules will affect our pressure. The more molecules we have, the bigger the pressure. So it's not mass. It's looking at the number of particles.
Moles?
Why moles and not molecules?
Because it's
A molecule is too tiny for us to measure, so we always measure in the mole because we have a larger amount. So our last relationship is looking at the moles being directly proportional to our pressure. Okay. Everything we've written out so far is a single letter symbol except for moles. So we want to come up with a new symbol for moles where we don't have to use 3 letters. As a hint, it refers to the number of particles. N is directly proportional to our pressure. Okay. Each of these observations, and in fact there's a few others because we can tie temperature to volume, we can try moles to volume. Each of these relationships and the discovery of that relationship gets named after the person that initially discovered it. Okay, so your textbook lists out Charles' law, Boyle's law, Avogadro's law, Henry's law. Right? There's all these named laws. All they're looking at is the individual variables and how they ultimately affect pressure. That's the only reason they're there. Okay? So, if we go through and quantify, we get all these nice little relationships that come out of it. And ultimately what we can end up doing is that someone went through, took all of these different variables and put them all together into a single plot, and they noticed that it varied with a constant. That constant they defined as R, which they said was the gas constant. Why? Because we're looking at the gas phase. So this constant is ultimately a conversion factor that allows us to convert pressure to volume, moles to temperature, moles to volume, moles to pressure. We can convert now between 4 different things by knowing some information about our gas. Massively important conversion factor. That's the biggest thing that you get out of the gas law, is R and that relationship. So whatever gas we are looking at, we can solve for R. We can change the type of gas, we can change the temperature, we can change the pressure. But that equation will always hold true. The gas constant is always equal to the pressure of your gas times the volume of the gas divided by the moles divided by the temperature. Okay. What units do we need to use for temperature? Kelvin. How do you know it needs to be Kelvin? So there's a couple big reasons. Number one, if we look at the equation I gave you, what units do you see for temperature? Kelvin. Okay, so now the question, why do we use Kelvin? Somebody mentioned the other option. No, not because of 0. If we use degrees Celsius or degrees Fahrenheit, we have negative values. If I plug in a negative value here, is that going to work? No, something else would have to be negative. I'd have to have moles be negative, or pressure negative, or volume negative, and we can't do that.
Or is it also, if you use Celsius, you may have a 0, and then you'll be dividing by 0.
Which ultimately comes to the absolute scale of Kelvin, and we'll talk about that as one of the last things. That, yeah, theoretically we can't get to 0 degrees Celsius. Or Kelvin.
Celsius instead.
Yeah. And you've got to be a little bit careful about the mathematical inequalities with dividing by 0.
We can't
There's,
get to 0?
yeah, you can't get to 0.
What?
Mathematically, it does not make sense. If you make Kelvin, your temperature, equal to 0, I don't care what your pressure is, your volume, or your moles are, you'd be having some number divided by 0. Punch it into your calculator. What does your calculator tell you? It says you're an idiot. Stop dividing by 0. Okay? Pretty darn close to that. It's a little bit better than that. Okay? It says error undefined. Ultimately, what it's saying is it cannot calculate dividing by 0.
So, like, absolute 0 is what people mean by, like, just impossible?
So when we're talking about absolute 0, that has to do with temperature on the Kelvin scale, and we'll talk about that a little bit too. Okay. Yeah, there's all sorts of weird quantum mechanical things that come out of that too. Right? So, big deal with your R is I can now calculate the pressure for any substance if I know the moles, the temperature, and the volume. Because R is a constant. It will always be that value, 0.0821 atmospheres times liters over moles times Kelvin. So if I know any 3 of my 4 possible things, I can determine what the 4th is. Okay, so we can throw all sorts of different solves at you, and we can bury those conversions or those units into different things, and everybody gets confused and says they don't know what they're doing. So what you should do with every question that you see, write down pressure and write down the number. Just give me a P equals number, V equals number, T equals number, N equals, oh, I don't know what the N is. Guess what you should solve for? The moles, and there you go. Okay. So take the word problem and just convert it into what those individual symbols mean, and you should be able to solve relatively easily. The other big thing that comes out of this is that I can now compare 2 systems. If I start with conditions, have an initial condition, and I change the conditions in B, I can now solve for one of those terms. Because R under conditions of A will be what in R under conditions of B? The same, because R is a constant. So I can set those 2 expressions equal to each other and solve for whatever that unknown variable is. Right, so it's kind of a neat process. The most common way that students, or at least I've memorized that expression, is this PV equals nRT. Or if you get really creative with your spelling, you've got pervert. No. I never saw that. Wow. I was going to say pivnert, but you know. Pervert.
That's good. Like
As long as you remember the relationships, I keep hitting that. The relationship between those, PV equals nRT. Right? I had a science teacher actually put that on her license plate. And then she even got out the Sharpie and put an equal sign in between. And then she got pulled over because you aren't allowed to adjust your license plate, apparently. She was like, come on, officer, it's just pivnert. Like, I have no idea what you're talking about, woman. Step out of the vehicle. So, volume of a container is doubled. Assume the temperature and the moles are not changed. What happens to the pressure? So we got a couple ways that we can approach this. Anybody know what it is off the top of their head?
It doubles.
Volume of the container is doubled. What happens to the pressure?
Oh, wait, yeah, never mind. That goes down. My baby.
It's going to half. Remember, they're an inverse relationship. Okay. If you don't see that right away, that's fine. That's where I would argue these conditions can come in handy. Volume of a container is doubled. So really what we've got is an initial volume, an initial moles, whoops, another initial volume, so let's try that again, an initial temperature, and an initial pressure. Okay. We aren't told what any of those those numbers are, but we are told a little bit more information. Okay. We are told that our final volume is what? Doubled from what? our initial. So how do I show that mathematically? 2 times my initial volume. What is my final mole? It's the same. What is my final temperature? What is my final pressure? At this point, we don't really know, so we can say, what is that? So now what we can go back through and do is use our expressions from above. Whoops, that's an eraser. Our initial pressure, whatever it is, I don't know what it is, times my initial volume over my initial moles times the initial temperature. What is that equal to? My final pressure, my final volume, what did I say my final volume was? 2 times my initial volume divided by my initial moles, which were, or sorry, my final moles, which was same thing as my initial moles, times my final temperature, which was same thing as my initial temperature. All of those variables, how can I possibly solve? Well, I need some more space here, so I'm going to have to erase that. How can I group some of these? How do I get the moles all on the left side of the equation? What do I have to do? Multiply both sides by the initial moles. So now I'm effectively doing algebra. What's the initial moles divided by initial moles? They cancel out. How do I get my temperature all collected on one side? Multiply both sides. What happens to my temperature unit? Cancels out. How do I get my volume all on one side? I can divide both sides. What happens? My volume units cancel out. All right, there's a lot of stuff canceling in there, so let's go ahead and rewrite that. On the left-hand side, what do we have left? We only have P initial. What do we have on the right side? 2 times P final. What were we solving for? P final. What happened to P final? It's exactly half of our initial. So some of you could do that in your head, that's fine. Okay. What we're going through and doing for any of these systems is this comparison. Sometimes we'll give you all of those numbers. Personally, I hated when I was given all of those numbers, because then I have to do all of that calculation. If I'm given a system like this, I can just cancel the crap out of everything and it simplifies. I don't have to worry about doing anything in the calculator. 151, you'll go through a lot of these type of calculations, looking at those relationships, a lot of those conversions. It's super exciting. I can't wait to have you guys jump into that. Thankfully, I don't have to deal with that. I mean, dang it. That was dumb. Questions? Okay. Okay, when solving a question like this is what I've already started to outline at the bottom. Convert any information you've got into just the variables. So you've got that information down in front of you as opposed to trying to think about it out of the word question. Get that information down first. So we know the pressure is 1 atmosphere because we're told STP, and STP stood for standard temperature and pressure. Standard pressure is 1 atmosphere. So my pressure is 1 atmosphere. Volume, 2.34 liters, given to us in the question. Temperature, 273 Kelvin, because standard temperature is 0 degrees Celsius. And how do we convert Celsius to Kelvin? Add 273.15. Our R value, which you've already seen how well I've memorized it, 0.0821 liters atmospheres per mole Kelvin. Once we've got that information, it's now just rearranging pivnert to give us moles equals PV over RT. You'll notice that I've rearranged that even further. Right? So this is actually 2.34 liters. Our pressure is 1 atmosphere divided by 0.0821 liters times atmospheres per mole times Kelvin times, that's a 273 Kelvin. What happens with our units? Liters cancel, atmospheres cancel, kelvins cancel, and I get 1 over moles, which is moles. Okay? So my units check out. I did switch this around ever so slightly, and I would like somebody with a calculator to go through and do this calculation for me. Do not use the 2.34, but I want you to take 0.0821 times 273. And then do 1 divided by that number. What do you get?
Yeah, there's a calculator.
1 divided by 0.0821 divided by 273. Times 273. Return. Now do 1 divided by that number. Oh, wait.
No, it's divided by 1.
Did I solve that equation wrong? I solved that equation wrong. Here, let me fix this. Anybody notice the algebra mistake? Take a closer look. Your equation is PV equals nRT.
Yeah.
What's the algebra mistake? What is n equal to? Yeah. This is RT. Did I have it right the first time? Oh, no, I did. Never mind. PV. RT. Did I do it? Hurrah! Stupid gases. Let's try that again. PV. Yes, I said hurrah. Find out it's 22.4. 1 over 22.4. What is 1 over 22.4? R times T was 22.4. Our units come out of that as moles per liter. Where is that conversion from? From that thing earlier. 1 mole is 22.4 liters when? At standard temperature and pressure. Where did 22.4 come from? The ideal gas law. It's just a manipulation of the ideal gas law at a very specific temperature, at a very specific pressure. It is one and the same. Okay? There is no 22.4 nonsense they tell you to go through and memorize. It is the ideal gas law. All it is you picked a single temperature and you picked a single pressure. Why did they pick that temperature and that pressure? Why would you pick 1 atmosphere? Where are most science happening? On Earth and very close to sea level. So under most of our experiments, our pressure is pretty darn close to 1 atmosphere. So that's why we picked that standard pressure. What's going on with the temperature? I got no explanation for that one. They just decided to pick 0 degrees Celsius just because they liked 0 degrees Celsius. Okay. Does it make sense to have a standard temperature be a temperature that we don't typically run our experiments at? No. Which is why if you talk to an engineer and ask them what STP is, they'll give you different standard temperatures and pressures. Awesome. Depending on your field, the standard changes. Okay? So if somebody tells you, oh, this reaction was run at STP, you might want to ask, what do you mean STP? And when they tell you, oh, standard temperature and pressure, you know, what temperature, what pressure? Because depending on what you are running and working with, those variables will change depending on what your conditions are. Okay? One of the last things that we can look at is Dalton's law of partial pressures. You can take your individual gas particles. Remember, one of our assumptions was that there was how much attraction between each of our gas particles? 0 attraction between gas particles. What happened when the particles collided against each other? They bounced right off with no loss of kinetic energy. Okay? Everything's maintained. Okay? So if I add more gas particles into a system, okay, or different gas particles into a system, they're going to be colliding with the walls much the same as any other gas would be. So one of the things that we discovered with this is that if we add up the partial pressures of each of the individual gases, that will equal the total pressure within the individual system. So I can have different gases, but I can then solve for their pressures through this system or through this relationship. And that is Dalton's law of partial pressures. So all you got to do is add up the pressures of each of the gases. That gets you to your total. What if you're given the total pressure?
You work backwards.
Work backwards, you're probably being asked to solve for one of the other pressures. So you're just rearranging this equation, solving for whatever you want out of each of those individual systems. Okay? So you typically see a big glut of information within this. Partial pressure of helium is 125 millimeters mercury. Plus, I need all the numbers. Neon is 45 millimeters mercury. Plus, oh my gosh, there's way too many gases in this.
158.
158 millimeters mercury for argon. 17 millimeters mercury for krypton. If I add all those numbers together, I now have the total pressure. So really simple, all you're doing is adding that together. It's a question that tends to freak most students out because you have a glut of information, tons and tons of numbers. In most cases, all you're doing is adding those numbers or subtracting those numbers. Okay? So it is usually a straightforward question. It can be combined with other gas law stuff to make that a lot more challenging. At most one.
Is it Superman?
Last thing we'll address, not krypton, but absolute zero. One of the things that kind of comes out of our ideal gas law is that we can extrapolate backwards on a plot of volume versus temperature or pressure versus temperature, and we can find that we will have 0 volume when we have 0 temperature. So all that really ends up saying is that at absolute 0, everything ceases to move. Okay? We have no volume and everything disappears. Okay? Kind of a neat little process. What makes this even more interesting? Guess what scientists have done? They've achieved negative kelvins without passing through absolute 0.
Wait, what?
Yeah, that's a challenging one. So if you play around with thermodynamics, the laws of thermodynamics, you can create a system that actually achieves negative temperatures, negative kelvins. It's ultimately a mathematical manipulation more than anything else, but it's a kind of a neat system to go through and do.
If you theorize